So the first classifier, the first detector algorithm that we're going to be looking at is called, it comes under Cascade classifier, and it's called Haar Cascade classifiers. So I'll just quickly read out the formal definition. It's available on a lot of websites, including Wikipedia. So a Cascade classifier, or namely Cascade of boosted classifier, works with Haar-like features, is a special case of ensemble learning called boosting. So in machine learning, there are two very famous techniques called bagging and boosting. Boosting is one of the techniques. So it basically means combine multiple weak learners to form a strong learner. It's a very famous idea, and it has been used, and it is still being used today. And there are various variations of this idea available. So I'll just cover that in detail in a little while. It typically relies on Adaboost classifier, again one of the boosting algorithms. It's Adaboost, just like Logic Boost or XGBoost. If you are a Kaggle user, you might have heard a lot about XGBoost. It's used for Kaggle competitions. Almost all of the winners use that. Cascade classifiers are trained on a few hundred samples of the image that contain the object that we want to detect, here in our case a face, and other images that do not contain the images. Okay, that's it. Negative and positive examples. Nothing too fancy here. So how to detect a face in the image? So we are using algorithm firstly proposed by Euler-Jones. It's called Euler-Jones Object Detection Framework. And here are the steps. The original paper was published in 2001. Oops. Yeah. So here are 4 steps we will go through. First of all, we select some features that we want to use to detect faces. Features are basically filters. If you are familiar with convolution neural networks, those features are similar to here the Haar features. Then create an integral image. We look at that. It's basically an image where calculating the coordinates is much more cost effective. We'll look into it. Then the Adaboost training, we will select the desired number of features. These Haar features, we will select the desired number of features which themselves will act as weak learners, and will combine them to form a strong learner. So we will select X amount of training features. So how do we select those features? We'll use Adaboost for that. So Adaboost will select, these are the best classifiers, the top X classifiers, and X is your arbitrary input. And then we'll use that to perform classification, and they will be called cascading classifiers. So these are the 4 steps that you need in order to perform Haar cascade classification. Okay. So first of all, Haar feature selection. How do you select features? So it has been observed, and it was observed at that time, that there are some common features that we find on most common human faces. And this, by the way, is an image taken from a blog, which I have linked below. So there are common features in human faces, such as a dark eye region compared to the upper cheeks, a bright nose region compared to eyes, some specific location of eyes, mouth and nose. So these are specific features that exist in all faces. So we can extract these features using filters. So filters are nothing but a matrix of values. Just for example here, so those values, here is one filter, right? So it is trying to detect the edge of eye. So here are vertical and horizontal filters. Different filters are trying to predict different kind of features. So in this example, the first feature measures the difference in intensity between the region of eyes and the region across the upper cheeks. This value is simply computed by summing the pixels in the black area and subtracting the pixels in the white area. So if the difference is really high, that means you have got an edge. So it will basically calculate the difference between the white region and the black region from the image. So if the difference is really high, what that means is that the both of these parts of the filter, which is the dark and the light part, got activated, which means the face cover, the area which the filter is covering contains both of the parts. So this will result into high value of the difference of both the parts, which means the filter got activated. So which means that we have detected an eye. It basically means that. Then we apply this rectangle, which is the filter, as a convolution kernel over the whole image. That's what I said about the terminology related to convolution in neural networks. In order to be exhaustive, which means in order to use all different variations of all different filters available, we should apply all possible dimensions and positions of each kernel. A simple 24 by 24 image would typically result in 160,000 features. This is the calculation that they have done. We can easily do that by it's just simple mathematics. I won't go into that in detail, but if you want, you can just calculate that, or it's easily available on the internet on the research paper. So we can, well, if you want to be really exhaustive, we have 160,000 features. Now, it would computationally be impossible for live detection. So how do we speed up this process? How do we reduce number of features? How do we speed up this whole process of calculating the features? So one good region, so there are basically two steps. Once a good region has been identified by a rectangle, which means when a rectangle gets activated, when a filter gets activated in a particular region, that is a good region. So when such a region is identified, it is useless to run a window over completely different region of the image. This can be achieved by Adaboost. We'll look into that. So it's basically saying is that if you once recognize that a face only occurs in a particular part of the image, it's just useless to run the filter on a different part, which is not detected, which is not given any signs of it containing face. Now compute the rectangle features using integral image principle, which is way faster. Now we'll cover this next. So integral image, so what it's talking about is we need to calculate the sum of the pixels in the black area and sum of the pixels in the white area. So performing this calculation, it is much easily done using integral image. So I'll just quickly show you what the integral image is, but before that, let's just see what happens next. Let's assume that you have calculated both the things. You have reduced the number of features and you have made the calculation of the rectangular feature much faster. Now what happens? Now that features have been selected, we apply them on a set of training image using Adaboost classification. That combines a set of weak classifiers to create an accurate ensemble. So once we have selected the features, those features in themselves are very weak classifiers. So we'll combine them to form a really strong classifier. So with just 200 features instead of 160,000, the accuracy of 95% is achieved by the authors of the paper. In their example in the paper, they have selected 6,000 features. So just selecting 200 features, 95% of accuracy can be achieved. So this is really amazing, right? So now let's just see both the steps. First, I'll just quickly walk you through what an integral image is. The definition basically is an integral image is an image that we get by cumulative addition of intensities on subsequent pixels, both horizontal and axes. We rely on features specific to certain region of the entire image. Hence, we need properties of those specific regions. So we'll basically cumulatively sum the values of pixels both horizontally and vertically. So let's look at what integral image actually is. So here's a website that just explains that. I'll link that also in the notebook. Now, basically, an integral image. Now, basically, let's suppose that you have this as an image. So, image is just a matrix with where each value is representation of the pixel intensity. So, let's assume that you have this as an image. Now, to convert this image to its integral image form, you need to have at every position the value of that should be cumulative sum of the previous values both horizontally and vertically. Now what does that mean? So let's say right here you are trying to convert this into an integral image. So which is this, the final resultant, but we'll look at how it is done. So the part in green has actually been converted into its integral form. So it's basically showing the progression of the algorithm. So an algorithm basically means, so the algorithm basically states that the value of integral image at coordinate x and y is the value of image at x and y minus the value of that image in the integral image of x minus 1 and y minus 1 coordinates, and again add the integral image position of x and y minus 1 and x minus 1 and y. So basically, so let's just see that algorithm in action. So the obvious results are 1 plus 5 if it is a cumulative sum of all values before it. So here we only have vertical value, which is 5 plus 1 6 right here, and here this should be 1 plus 2 3. Now 14, let's just see how this 14 results. So, or better yet, let's just see how this 7 results. By the way, we can see 14 by, if you add all of these 4 values, you will get 14. So 14 is the sum of all the values cumulatively, both horizontally and vertically. Now let's apply this algorithm that we have learned right here to calculate this 24. So we need to calculate the value at position 2 1. So here they are taking this position 7 as position 2 1. So according to the algorithm, what we need is basically we need to add the value of pixel in the original image at this position, so which is basically 7. So we add 7, which they have done right here. They have added 7. Now subtract x minus 1 and y minus 1 coordinate, which is 3. 1 minus x and 1 minus y. So 3, subtracted 3, and then add x minus 1, which is basically rho minus 1, which is this 6, and add 14. So after applying this algorithm, you get 24. In this way, calculate the entire image. In this way, just repeat the operations and calculate the entire integral image. Now after that, once we get this integral image, where is it? Yeah, this is the integral image. So first row, we have added one row and one column of zeros, so the calculation is really easy. Now, let's say that you want to calculate something. Let's say you want to calculate the average of a feature, the average of a filter that is of the size n by n. So you need to repeat the loops. You need 2 nested loops for that. And the complexity, if you have read anything about the time complexity of algorithms, the time complexity will be big O of n squared if the size is n by n. Otherwise, it will be big O of mn if the size is m cross n. Now that is really expensive. Now the whole point of converting the image to integral image was to reduce this calculation cost. So now, if you already have integral image, let's say you want to calculate again this the average of this filter. So in the normal image, that would take n squared time, but if you want to do the same thing in the integral image, that would take only constant time. So how does that do? How does that take only constant time? So let's just see. Let's say you have this is the area that you want to calculate the average of. So let's mark the extreme values by A, B, C, and D. So A is 1 row and 1 column before the starting pixel. So A, B is the extreme value, C is again the extreme value on the bottom left. Now D is the last value that you want to calculate. Be really careful about this D. This D is the part of the feature matrix. Now the simple algorithm is that you need to calculate the sum basically is D plus A minus B minus C. So let's just verify that. 46 minus 0 is 46. Again, minus 0 minus 7 results in 39. And again, if you sum all of them, you get 39. So we have done only 4 operations, that is constant number of operations for calculating something like this. Now the filter can be as large as possible. The image can be as large as possible, but you only need constant time. Whereas this operation will grow by n squared if you only use normal image. So this is the usefulness of the integral image. All right, moving on. Let me just quickly turn this into full screen. Yeah. So now that you have learned how to use integral image, let's move to Adaboost. This is how we will select 200 features or X number of features out of these possible 160,000 features. So how to do that? Now, this is the Adaboost algorithm. I'll just quickly go over that. So I'll just hide all of that because this seems too much intimidating. It's really easy algorithm. It's really straightforward. Now we won't implement the algorithm from scratch, but there are a lot of good implementations available on the internet. You can just read them out. It's really simple if you know anything about random forest or decision trees or whatever. So let's just say you have an input of size. Well, you have an input set of size n. So you have n input sets, input points or data points. Now you want now let's just say you have a set of weak classifiers, in our case 160,000 weak classifiers, and you want to select X amount from them. You want to select X weak learners and combine them to form a strong learner. That's the output. That will be the output, the set of combined weak learners that will act as a strong learner. Now, you have the data and you have to map the data to a particular class. If you do it right, that's +1. If you predict wrong, that's -1. Right. Now, what we do is we first of all apply weights to particular example, particular data point. In the beginning, all the data points are given equal weightage, so equal importance. That is 1 by n. N is the number of data. So repeat that t times. T is basically a hyperparameter, how many times you want to train a weak classifier. That many times you will get a particular classifier, a particular weak classifier. So that is the set of weak classifiers that will get, the size of the weak classifiers. Okay. Now choose a particular weak classifier that is denoted by a small ht and train that. So basically here ht can be viewed as a decision tree with just one node, if you know what decision trees are. So we compare one particular value, one particular feature, right? And in this case of Haar cascade classifier, this is just one feature, one filter. Now calculate the error. So this equation basically calculates the number of wrong classifications made divided by total number of classifications made. Now here alpha of tth step will calculate the importance of this particular classifier, particular weak classifier. So this value of alpha will be really high if you have made a really low error. So as you can see, 1 minus error divided by error. If the error is really low, this value will be very close to 1. So if the error made is really less, the value of alpha, which is the importance of this particular classifier, will be really high. So now what you have to do is you have to provide more weightage to the data that has been classified as a wrong class, so that next time the next classifier has to work harder to classify those examples. Now how do we do that? So we basically reassign the weights, and the formula that we will use is, we'll say that whatever the previous weight was, just multiply it exponential times the negative of the importance into the multiplied by the prediction made. So the prediction will be 1, which is positive if it is correctly predicted. So the final value will be multiplied by the negative of the exponent, which is really less. So if we have classified the data correctly, the value of the weightage of that data, the importance of that data will be really less, because it is multiplied by a negative exponential. Now if we have made an error, that means the hypothesis is -1. So what happens is minus and minus, negative and negative become positive, and the weightage will be multiplied by a positive exponential value, which means the weight will automatically increase. So in this way, you have increased the weight of all the data points that have been classified incorrectly. Now you randomly select weights based on their probabilities. Finally, you randomly select the data for the next epoch, for the next loop, randomly based on the probabilities. So the data which has really high weightage will be taken into account multiple times. In this way, the algorithm will work much harder to classify the data which it couldn't classify previously. And you save this particular weak classifier in a set. Now finally, when you have t weak classifiers, that was our intention, t best weak classifiers, then you just return that. So in this way, this is the basic algorithm of Adaboost. This is how it works. There are multiple variations using different algorithms, different weak classifiers, but this is the basic idea. You provide equal weightage to the data, you select a weak classifier, compute the importance value, that is the alpha, then you redistribute the weights of each particular training example based on the fact whether they were classified correctly or incorrectly. Incorrectly classified data set incorrectly classified data points are provided more weightage. And finally, well, the last line that I missed was basically you have to normalize the weightage of a particular data. That is really nothing really special about it. So this algorithm is taken into account to choose. Something that I'd like to mention is that this classifier Haar cascade doesn't work really well, but the steps needed to implement this, which is such as Adaboost and integral images, all of these things are really important in image processing. That's why this is one of the longest video in this series. This is one of the longest concepts in the series, but you're not going to be using this particular classifier, but these concepts such as Adaboost and integral image, these are really important. These you will use in your career as a computer vision engineer. So Haar cascade in details can be read in this particular blog that I really like, and more Haar features are available on OpenCV. So basically, different Haar features, as I've already said, that the features for Haar cascades are called Haar features. So these features are available in different sets. So for detecting faces, there are different features. They are best extracted features after applying Adaboost classifier. So all of them are available with different names on OpenCV in OpenCV library. So you can just check them out. Here we are using frontal face detection, so we'll use face Haar features. So that's it for the theory of the algorithm, how this actually works. Now we'll move on to code.